Namaskaram. In the coming three sessions, we will discuss some properties of Fourier transform and related problems. This is our first session. Okay, first property, the linearity property. This is similar to the linearity property of Fourier cosine transform and Fourier sine transform. Okay, and this property states that Fourier transform of a into f of x plus b into g of x is equal to a times f of x plus b times f of g of x, where a and b are constants. That means they are numbers. Okay, so we can easily prove this result with the help of using the definition of Fourier transform. What is the definition of Fourier transform? What is Fourier transform of f of x? Yes, this is the definition. By definition, Fourier transform of f of x is equal to 1 by root 2 pi integral minus infinity to plus infinity f of x e raised to minus I omega x dx. Okay, this is the definition of Fourier transform. Okay, next we are going to just apply this definition on this function afx plus bgx. So we are going to replace this f of x by this function a into f of x plus b into g of x. So what happened? So this expression become like this. So Fourier transform of a into f of x plus b into g of x is equal to 1 by root 2 pi integral minus infinity to plus infinity. Instead of f of x, we use this function, this big function. Okay. So a into f of x plus b into g of x into e raised to minus I omega x d. Okay. Next, we are going to split this integral using this plus sign. So what happened? We can split this integral as like this. Because 1 by root 2 pi is common. So 1 by root 2 pi integral minus infinity to plus infinity a into f of x into e raised to minus I omega x dx plus 1 by root 2 pi integral minus infinity to plus infinity b into g of x into e raised to minus I omega x dx. Okay, so we split this integral using this plus sign. That's all. Okay, here a and b are numbers, they are constants. So you can take outside from this integral. So what happened? So this become like this: a into 1 by root 2 pi integral minus infinity to plus infinity f of x into e raised to minus I omega x dx plus here this become b times 1 by root 2 pi integral minus into plus infinity g of x e raised to minus I omega x dx. Okay. Then what about this portion? 1 by root 2 pi integral minus infinity to plus infinity f of x e raised to minus I omega x dx. This is nothing. This is exactly our Fourier transform of f of x. Clear? Similarly, what about this portion? B times what? B times, this is nothing. This is exactly the Fourier transform of g of x. Okay. So ultimately, the Fourier transform of AF plus BG is equal to A into Fourier transform of f of x plus B into Fourier transform of g of x. This property is called linearity property of the Fourier transform. Okay. Okay, next problem is another property, shifting property or time shifting property, because there are two type of shifting problems out there. Fourier transform of f of x minus a is equal to e raised to minus I omega a into Fourier transform of f of x. Okay. As similar to the previous case, first we are going to apply the definition of Fourier transform on the function f of x minus a. So what happened? We are going to just replace this f of x by f of x minus a. So by definition, this is the Fourier transform of f of x minus a. Clear? 1 by root 2 pi integral minus infinity to plus infinity. We just replace f of x by this function f of x minus a e raised to minus I omega x dx. Next, we are going to apply a substitution for simplifying this integral. The substitution is u equal to x minus a. This is our substitution. Okay, we are going to replace this x minus a by u. So what about du? So du become dx because a is a constant, so it's differentially 0. And next one, what about the range of this u? It's clear that x is varying from minus infinity to plus infinity. So what about the variation of u? Whenever x equal to minus infinity, this is minus infinity minus a number. So again, still it is minus infinity. To what about the upper limit? Whenever x equal to infinity, this is infinity minus a finite number. Infinity minus finite is again infinity. Okay, infinity means very very big. Okay, very very big minus something a finite is again still very big or still infinity. That's a property of infinity. So anyway, infinity minus a quantity, a finite quantity, still infinity. Okay, so the variation of u is minus infinity to plus infinity. Then one more thing is there is a term e raised to minus I omega x. So we have to replace this x in terms of u. So what is x? So from this expression, x is nothing, x is equal to u plus a. Okay, now everything is clear. Okay, now we are ready to replace this integral in terms of u. Okay, so what happened? So this become 1 by root 2 pi integral minus infinity to plus infinity, that is the range of u, and x minus a become u, that is f of u, e raised to minus I omega into what about x? X is u plus a, u plus a, u plus a, and dx become du. Okay, so this is our integral. Okay, next we can split this e raised to minus I omega into u plus a as product of two terms. What is that? That is nothing, e raised to minus I omega u into e raised to minus I omega a. Okay. Okay, that is it. We can replace this one term using product of these two terms. So it is clear that this second term means e raised to minus I omega a. This term is constant with respect to u. Clear? E raised to minus I omega a is constant as a number, like a number with respect to u, because this integrand is with respect to u. So we can take outside. We can take this term outside this integral. Okay, so this integral become like this, e raised to minus I omega a 1 by root 2 pi integral minus infinity to plus infinity f of u. Instead of this entire term, it remains only one term, that is the first term. First term means e raised to minus I omega u, this term, into du. Okay, what about this integral representation? 1 by root 2 pi integral f of u, this one. What about this one? Okay, this is exactly our Fourier transform of f of x by definition. Clear? Only change is here the independent variable is u instead of x. That is not a matter because this is a definite integral. Clear? This is a definite integral. So whatever be the variable, no problem. Final result, final answer is remains same. So you can use either u or t, x, whatever be, no problem. It's a definite integral, so it's give the same answer. So this is exactly the Fourier transform of f of x. Clear? Because this is a definite integral. It doesn't depend the independent variable. So this is equal to e raised to minus I omega a into the Fourier transform of f of x. Clear? Hence the result. Okay, this is your homework. This is called frequency shifting because here we shift omega. Omega corresponds to the frequency. Okay, in the case of signal processing. So here the result is we have to show that Fourier transform of e raised to I a x into f of x is equal to f cap of omega minus a. We have to just replace omega by omega minus a. And what is f cap of omega? That is nothing. That is the Fourier transform of f of x. So here we assume that this is not. Okay, in this problem we assume that we know this Fourier transform of some f of x. Maybe this f of x is a very simple function or non-function. Okay, using that Fourier transform we can easily find the Fourier transform of e raised to iax into f of x. So we have to just replace omega by omega minus a. Okay. So this is your homework. Thank you.